So, hello and welcome to my talk. On June 4th, 1996, European Space Agency's spaceport in Kourou, French Guiana, was getting ready for a launch. The expectations were high because this was not just an everyday routine launch. It was the very first launch of Ariane 5, a completely new type of launcher, which was more powerful and capable of carrying higher loads than its predecessor, Ariane 4. So European Space Agency was putting high expectations into this launch. On board of the launcher was a payload of satellites of the cluster mission, which were to be positioned in the orbit to study solar wind and how it interacts with the Earth's magnetosphere. The launch was completely uneventful, everything went well, and the anxiety in the control center started to drop a bit, when suddenly, 37 seconds after launch, the rocket turned into a huge fireball, and pieces of those expensive scientific satellites were raining into the mangrove swamp surrounding the Kourou spaceport. This is the story of the line of code that crashed the rocket. When I first read about this bug, it seemed like a really straightforward case. The line of code in question was taking a variable that contained a 64-bit float and converting it to a 16-bit signed integer, and you already see where this is going: integer overflow, operand error, of course. When I thought of the guy who wrote this line of code, I felt like I wanted to tell him, dude, what were you thinking? Are you sure you should be working in the space industry? It's easy to point your finger and assign blame to a person. I was so angry at him for causing a multi-million-dollar failure, but just so a basic and beginner error. Remember this emotion of anger and blame, but we'll get back to it. So I'm sure you all already realize that this is not the whole story. Otherwise, this would have been a very short talk. So to understand the whole story, we first need to learn what was the line of code doing in the context of the whole spacecraft. So let me introduce the main protagonist of this story, the SRI, Inertial Reference System. That's basically a tiny computer that tells the ship where it is and where it's going. It's taking measurements from a bunch of sensors, gyrometers and accelerometers. It's doing a bunch of calculations on those measurements, and then it's passing the resulting navigational data to the main computer. There are two SRIs on board for redundancy. One is active, one is standby. Of course, the redundancy is in other parts of the system too, but that's not important for the story. So what happened on that fateful day in '96? All the sensors were doing its own thing, passing the values to the SRI. It was doing its calculations, and one of the intermediate values in the calculation was a variable called horizontal bias. And at some point during the flight, the value that was coming in from one of those sensors became bigger than what was the safe value to fit into the horizontal bias variable. And the code threw an operand error. At this point, the SRI would have switched over to the backup unit, but that one was receiving the exact same measurements and running the exact same code, so it has already failed 70 milliseconds earlier. So the active SRI had no other option but to also call it a day. And before it switched off completely, it sent a bunch of diagnostic data down the message bus. The onboard computer received this data, thinking it's just another batch of navigational data. And it basically started screaming, oh my God, I'm 90 degrees, of course I need to do something about it right now. And it issued a sharp and aggressive course correction, which was that sharp turn to the left you saw in the video. At that point, the ship was going close to the speed of sound, so it quickly started disintegrating under aerodynamic forces, and that triggered the automatic self-destruct system, which detonated the spacecraft. So we know that this was not a simple developer oversight, so what was going on here? Well, we need to realize that the SRI was developed in 1980s. And back then, computers were really expensive and weak and really not powerful devices, and computational power was at a premium. So the requirement for the development team was that the computational load on the SRI must never exceed 80% of its maximum computational capacity. And because of that, the developers had to go over the code line by line, basically prune everything that's not needed and that's not absolutely essential to run the spacecraft. The SRI was in total working with 10 variables. Out of these 10 variables, 7 were protected against overflow. But for 3 variables, the developers did a detailed analysis and determined that under no conditions in flight can the values provided by the sensors reach the dangerous levels or dangerous numbers. There was enough of a safety margin that they were completely sure that the values are safe and the overflow can never happen. So they decided to not protect these 3 variables against overflow. I hear what you're thinking. If the variables could not ever overflow, how come the horizontal bias variable did overflow? To understand this, we need to take a look at the whole Ariane series. These are Ariane launchers 1 to 5. The crash happened on Ariane 5, but that was actually not the spacecraft that the SRI was originally developed for. It was developed for its predecessor, Ariane 4. It was in operation in there for many years already. It was deemed to be proven by operation to be completely safe. So they just took it and plugged it into Ariane 5 as it was without any major changes. If you look at these 2 spacecraft, if you look at these 2 launches side by side, you can see on first glance that they're a completely different piece of hardware. Ariane 5 is more powerful, it has more higher acceleration, it's capable of flying a steeper trajectory. So the values that were coming from the sensors were also completely different. And this is something that the development team did not account for, and that is what caused the overflow. So we can already see that there were some assumptions that played into making the bug happen. The developers who created the original SRI assumed that the type conversion will always be safe. And in fact, they were so certain of that that they did not even document this as an operational restriction of the SRI. But why was the code even running in flight? Because, it shouldn't have been. To understand how this is possible, we need to learn about what is called an alignment sequence. And I'm going to massively oversimplify here because I'm no rocket scientist. But essentially, as the rocket is standing on the launch pad, it, at all times, needs to know which way is up, which is not as trivial as it might sound, because the directional information is provided by gyroscopes. These point in the same direction in space, regardless of how much the spacecraft is rotating around them. But the problem here is that the spacecraft is standing on the launch pad, and the launch pad is on Earth, and the Earth is rotating. So we need to account for the Earth's rotation, otherwise the spacecraft would think that this way is still up, and that would not do well for navigating the spacecraft, because if the rocket was standing there for just 3 hours, the Earth would rotate by 45 degrees. So for this purpose, the alignment sequence is basically accounting for that on a continual basis, adjusting for Earth's rotation so that the spacecraft knows how to use the values provided by the sensors. Usually, the ship is in alignment mode up until 10 seconds before launch, at which point it switches over into flight mode, and that is on basically for the whole duration of the flight. However, on Ariane 4, the development team decided to create, I hesitate to call it a feature, it was a hack. It was a hack to account for the possibility that the launch might be held back by 10 seconds, 20 seconds, a very short amount of time. If the alignment mode was not running anymore at that point, the ship would not be able to launch because the time window would be lost. And they would have to go over the whole alignment sequence again, which could take an hour or two, depending. So they decided to keep the alignment mode running for an additional minute to account for this possibility. It was actually used in one launch of Ariane 4, but this feature was not needed in Ariane 5, because Ariane 5 had a completely different countdown sequence. So it was really not needed, but they decided to leave it there because it was deemed safer to leave it than to start tinkering with code that was known to be safe and working. Basically, don't touch it if it's not broken. Side note, the alignment mode was running for about 50 seconds after launch, which is 40 seconds after liftoff, give or take, and the explosion happened at 37 seconds after liftoff. So we've got another assumption that was playing into making this bug happen. The alignment mode should be running after launch, even on Ariane 5. But why did both the SRIs fail? You remember this picture, how these guys both called it a day and switched off and did not even attempt to handle the failure more gracefully. Well, this was a requirement that the development team got from the team that was designing the whole spacecraft, and basically the logic behind, or the thought process behind this requirement was that any failure that could occur in the spacecraft is a hardware failure. So once the SRI throws a failure, it's not safe to operate it anymore, and it should switch over to the other unit. So the team was very concerned about hardware failure, very concerned about the hardware working, about hardware redundancy, but both the units were running the exact same software, and they did not account for the possibility of a software failure. Basically, the assumption was that software doesn't fail. I hear you laughing, but just take a step back and we might realize that we are all at times faulty of this assumption. For example, when you're working in a microservice environment, you are, of course, trying to handle all possible failures of your own microservice, but are you always thinking about the possibilities that one of the other microservices that are present in the environment might be down or might be providing something that you're not expecting? I think that we are all at times kind of guilty of thinking that software doesn't fail. My favorite part, as a tester, this is a question I often hear from colleagues, my fellow testers: why did not the testers catch this? They're the quality gate, they should catch all bugs. So, testing was done in two levels. First was testing of the SRI in isolation. We could call it component testing. It was using mocked server inputs that were generated by some electronic device and evaluating the outputs. And that was a very good, thorough testing. The team that was tasked to test the SRI was very thorough and did a really good job using Ariane 4's flight data. because that was what they received as specifications for the SRI. So we've got another assumption. The SRI should be tested with the same data as in the previous iteration. Then there was another layer of testing. That was testing of the whole navigational system end-to-end, basically. There were several possibilities considered for this type of testing. One of them was mounting the whole navigational system, including the accelerometers and gyrometers, onto some type of a mechanical thing that would move it in space, and this way provide positional input to the sensors. But that was deemed too expensive to build such a device. So then they considered testing it with mocked sensor inputs. But this testing team, which was, of course, a completely different team by a completely different outsourced company than the first team, the devices or the means that they had for simulating the sensor inputs, they feared that they were not precise enough, that they did not have enough precision to do a thorough type of testing this way. So they had a thought and said to themselves, wasn't the SRI tested already? We don't need to test it again, right? So they basically took it out and tested the whole system without it, with Ariane 5's flight data, but without the SRI. So we've got another assumption. The testing that was done already on the component was complete and thorough. Monitoring and observability. This is very much a side note because it didn't play any role into causing the bug, making it happen, but it did have big influence on how the bug was investigated and fixed. As a rocket is flying, it's of course sending some telemetry data to the control station. But in this case, right after the crash, when the investigating team analyzed the data, there was not just anything in those data that would tell them what was the cause of the crash. They knew that the main computer received some wildly inaccurate navigational information, but there was just nothing to base their investigation on. So they had to actually go into 12 square kilometers of swamp and find those two SRIs in the debris fall zone and hope that they are both intact enough so that they can get a memory read on them. All was well. In the end, they found them both in the swamp. They did get a memory read on them, but it was really just luck. It could have ended quite differently. So, and of course, it did slow down the investigation. The bug couldn't be fixed earlier. So, as we see, this was really a case of ADD, assumption-driven development. And if you take a look at these assumptions, you might realize that most of them, if not all, are caused by failed communication. The information that was needed did not get from point A to point B. The development team did not account for the fact that the SRI might be used in a different type of spacecraft, although I believe it was already known at that point. They did not think to pass the information forward by documenting this, so they basically failed to communicate it by means of documentation, which is why the next team fairly logically assumed that they are safe to keep the SRI code as it is with the alignment mode running into flight. The first test team did not get the correct test data for their testing, and the second testing team assumed that the first test team did get the data. Even number 4, that software doesn't fail, is to some extent a communication failure. Because when those developers got those requirements that said handle every failure as if it is a hardware failure, somebody might have come up and said, hey, guys, you're sure this is a good idea? You might want to reconsider that because we are software developers, so we actually know that software does fail. But as far as I know, this conversation never happened. So, as a wise man once said, the single biggest problem in communication is the illusion that it has taken place. This is a common problem on many software development projects. As you're taught to develop software, you are told to learn your programming languages, tools, technologies, AWS, Kubernetes, Docker, you name it. But nobody is ever told to approach the requirements with a critical mind. Question them. Find out the intent behind those requirements. Find out what are the people writing them actually trying to achieve. Communicating to those people, bringing out those hidden assumptions, and making them explicit and making sure everybody is on the same page. System thinking, understanding how your part of the software fits into the whole system and how a change in your part of the software can influence something in a completely different place. These are skills that are overlooked on many software projects. They are often not present at all, and if they are, they tend to be undervalued and underpaid. So let's get back to this guy. You remember him, he was so handy for being blamed. By now you understand that it was not actually this guy's fault. And if we had been blaming him, we would never have uncovered all the causes that played into making this bug happen. So how do we move past the blame? How do we make sure that we don't just point the finger at the most handy target and call it a day? Well, what's the most important factor to me is psychological safety. Blaming is, after all, just a defense mechanism. Just point your finger and assign blame in order to make sure that it's not you who's going to be blamed. So people need to be safe in their jobs. People need to feel safe that they're not going to be fired for making a mistake. People need to be safe that they're not going to be laughed at, ridiculed, yelled at. Cognitive load. Blaming is also an energy-saving mechanism. You point your finger and you're done with it, no other thinking required. So we need to make sure that people are not overworked, overloaded, burnt out, that they have enough cognitive capacity to do the thinking required for actually investigating the deep hidden causes. Good relationships on the team. If you hate somebody's guts, you're going to be very likely to point the finger at them and blame them. So definitely good relationships. And that does not mean that your teammates have to be somebody who has the same hobbies and you like to going for a beer with. No, I'm talking professional relationships. Our big topic, communication. There's this misconception on software projects that all communication between teams need to go through 3 levels of managers by the means of PowerPoint. Now, that is not an effective communication pattern, of course. So people actually talking to people. And feeling safe that you can talk to people, knowing who you need to talk to, and knowing nobody is going to be mad at you if you ask questions and inquire into people's thinking. A culture of embracing mistakes as a necessary part of learning process, as a means of how we grow. I have a friend who told me a story about how he caused a production outage for the first time, and the team invited him for a beer to celebrate. Your one was awesome. So this is the culture you want to cultivate on your team. And if you think about it, it's never that one guy's mistake. You always need to take the one step back and ask, what was it that enabled this one person's mistake to take down production. And how can we improve on that? Respect. A culture of where everybody feels respected for who they are, for how different they are, for the different skills and qualities they can bring to the success of the team. Trust. People need to feel trusted. They need to know that their colleagues are trusting them to bring their best to work every day, and that they can trust their colleagues to do the same. And finally, a sense of belonging. Belonging to something that's bigger than just me. A group of people that's working toward a common goal, building something amazing that wouldn't be possible if any of them would be working alone. So all of this I like to call company culture. And this is a term that is often misused and misunderstood. But as I understand this, in my view, a good company culture is a necessary prerequisite for building quality software. So what happened to the Ariane 5 project? Well, there was an investigation, these issues were found, and a couple others I did not have time to include into this talk. And the launcher was rebuilt. And it's relatively easy to rebuild a rocket if you have the money, but it's harder to rebuild trust. Once trust is broken, it takes a long time to rebuild. For quite some time, customers were preferring to use the Soyuz launcher for their payloads. But eventually, they started to trust Ariane 5, and it was going strong. Up until this day, there have been 116 launches of Ariane 5, of which only 2 were failures and 3 were partial failures, where the rocket did not reach quite the designated orbit height. So this is an excellent safety record for any launcher. The most notable launch was James Webb, that was carried out by Ariane 5. And the latest launch, as of now, was just about a month ago, satellites of the JUICE mission, which is right now on its way to Jupiter to explore Jupiter's icy moons, Europa, Ganymede, and Callisto, and investigate the possibility that there might be life underneath the ice crust, and study the possibility of colonizing these moons, which is all very exciting, and I can't wait to see where this brings us as humanity. Thank you. Any questions? French Guiana. I said Guinea. French Guiana. I think it was on the slide.
Why was it South America
Because it's closer to the equator, and the spacecraft gets a bigger angular momentum on launch, so it's basically a fuel-saving measure. Or you have to carry less fuel so you can carry higher payloads.
I just want to know, the countdown procedure where you get T-10 to 0, where it goes from 1 to flight mode, is that something that's still utilized today in today's rocket launch?
I have no idea. I am no rocket scientist. I presume it probably is, but last I read about it was on Saturn V. So, but I presume that every rocket that launches has to run something like that. Yep.
So company culture is like a sort of seen as a thing that's far away from a software engineer or someone on a team. You know, it seems seen as something that the company should build. Do you have any tips or tricks for how you could work towards better company culture?
I mean, it's hard for one person to go against the whole company. So either you change your job or you change your job. but yeah, trying to influence people in a positive way by just being a kinder person yourself and pointing out instances where it maybe didn't go as you thought. But I do not have a step-by-step recipe for you.
question and follow-up to that is, if you feel comfortable sharing about your own organization's company culture, do you find that in order to permeate strong culture, you're given space to practice those things that are often unseen?
Absolutely, absolutely. So I work for Showmax. Showmax Engineering sits in Prague, and the Prague team is absolutely amazing in terms of company culture. We're given so much space to just grow and be better people in there. I mean, it's not ideal, nowhere is, but it's pretty close to that. So,
And are you largely remote, or does it?
as of now, yes. Yep.
Do you think company culture is built by the team or by written in by management?
I think it's both. It's both the team and the managers, but managers, of course, have bigger influence. So, yep.
What was the train of thought that led you to read about this and draw these conclusions from the rocket?
So I wanted to do an analysis, because I love air crash investigations. So I wanted to kind of do an analysis of a famous bug. And Ariane 5 seemed quite convenient. And honestly, when I was submitting the abstract, I did not think what it was gonna lead me. I thought I knew what I was gonna talk about, and I was so wrong, because when I investigated it more deeply, I was surprised by these conclusions that I found in the report. So yeah, it's a very different talk than what I thought it would be when I submitted it.
You're saying that communication is really important in this sort of thing. People have very different experience. Like as a software developer, if you're like making software for a hospital, how do you like get the requirement, like without just the other person saying what the requirements are? Because you need like a fundamental understanding. You get that if you actually know nothing about it.
Well, I'm not working in healthcare, or so it's kind of a, let's say, an example that I know nothing about, but I understand what you mean, and I think there needs to be somebody on the team who has at least an idea of what the people are talking about. Because if you're developing something and you know nothing about what it's supposed to do, there's going to be so many misunderstandings. Yes?
As a tester, do you believe that there is such a thing as too much testing?
Of course. You gotta call it a day at some point. It's a matter of return of investment. So, and that's a tough call to make. At what point to just call the testing off and call it done, and any bugs that stay there, because there's always one more bug that they're just gonna make it into production. Thank you very much.